Okay, is this on? Hello? So it's a pleasure to be back in Beijing. I want to thank the organizers for putting together this wonderful conference and giving me the opportunity to tell you about some recent work I did with my student, Netta Engelhardt. So perhaps the most important result to come out of string theory in the past 30 years has been the development of a holographic theory of gravity. And one of the main questions raised by a holographic theory is, how does one recover the space-time metric from the dual theory? Well, of course, many people have worked on this, and in particular, there's been much work focusing on quantum entanglement, and in particular, the Ryu-Takayanagi formula for entanglement entropy. Since the entanglement entropy is given by the area of a minimal surface in the bulk, one might hope that you can then recover the metric, or at least the area of any surface in the bulk, by combining the entanglement entropies of various different regions on the boundary and subtracting and adding them in the right way. This was suggested in a paper by these authors and followed up by many people. This approach is still being developed. It now goes under the name of kinematic space and involves radon transforms and stuff. I think it works best in low dimensions, at least at the moment, and is somewhat indirect, and that you're trying to get the metric at a point, starting with something involving an integral of the metric. So what I'd like to do today is to describe a new approach. And this new approach is based on a special set of cross-sections or cuts of the boundary of an asymptotically anti-de Sitter space-time. So, of course, given the boundary manifold, there's an infinite dimensional space of space-like slices. But if the boundary is d-dimensional, there's a preferred d+1 dimensional set of space-like surfaces coming from the past and future light cones of bulk points. Basically, where those light cones intersect the boundary, you get a particular cross-section or cut of the boundary. And we'll call these light cone cuts. This is reminiscent of work that was done by Ted Newman back in the 1970s and 80s when he was looking at similar cross-sections of null infinity for asymptotically flat spacetimes. So the outline for this talk is that I'm going to begin by defining these light cone cuts more precisely and describing some of their properties. Then I'll show you how you can reconstruct the conformal metric. That's the metric up to an overall constant at each point just from the location of these light cone cuts. Then I'll complete the story by telling you how you can determine these light cone cuts entirely from the dual field theory without knowing anything about the bulk. And finally, I'll conclude with some discussion and open questions, including some ideas we're working on to determine the conformal factor as well. OK, so you can't actually use the light cone of a point to determine these light cone cuts because of gravitational lensing. So two null geodesics emanating from a point might end up crossing, and that's a caustic. And after the null geodesics cross, they actually become time-like. They enter a region which is time-like related to your initial point. So what we do instead is to define this set called the past of P. It's the set of all points Q such that there's a future-directed time-like curve from Q to P. And then the boundary of this past set is a null surface. And so we define the past cut of P to be simply the intersection of the boundary of the past of P with the boundary of the space-time. And the future cut of P can be defined similarly. These cuts are not going to be smooth because of the existence of these caustics. They're always continuous, but when you have caustics, there will in general be points where the cut is only C0 and not C1. So it won't be differentiable everywhere. But we expect that the places where you have these cusps are sets of measure 0, so, well, you'll see it doesn't cause a problem. OK, so here are some properties. The cut is always a complete space-like slice of the boundary. And there's a pass cut for every point in the future of the boundary, even inside black holes. So here's a space-time diagram of matter collapsing to form a black hole in global ADS. And a point inside the horizon still has a pass cut, a well-defined intersection of the boundary of its pass with infinity, c minus of p. Now it's interesting to look at a point outside the horizon, which I've labeled Q, which is way to the future of the collapse to form the black hole. If you look at the future cut of P, of course a lot of the future, the null geodesics from Q enter the black hole. The outgoing ones, of course, get out to infinity. So you might think you get only a little piece of a space-like surface, but property 1 says that's not what happens. And in fact, what happens is that the light rays coming out of the board just get gravitationally lensed and focused and end up producing a cut which goes all the way around to this side. Similarly, if you look at the pass cut of this point Q, you might think that, well, the outgoing null geodesics hit the boundary up here, and the ingoing ones you might think end up way down here before the black hole formed. But that would violate property 1 as well, because that would end up with a cut which is time-like. This point can be way to the future, these points are way to the past. That's a time-like surface. And the cut is always space-like. So again, what happens is that some of these pass-directed light rays just get gravitationally lensed and focused, and the pass cut is, again, a surface way up there. Okay, perhaps the most important property of these cuts is that two distinct cuts, C of Q and C of P, have one of the following property. To satisfy the following. So either they do not intersect at all, they intersect at precisely one point, or they cross, meaning that the intersection of the two cuts divides each cut into two connected pieces. And for this is true either for two past cuts or for two future cuts. In particular, this means that one cut cannot wiggle with respect to another and cross it multiple times, and also that two cuts cannot agree on an open set if they correspond to distinct points. Okay, so here's an example. The simplest example are the cuts of pure anti-de Sitter space. You can find these either by explicitly solving the null geodesics or by just symmetry. And I'll work in a conformal frame where the boundary is the standard static cylinder. And then you can easily see that if your bulk point is at t equal to 0, r at some r naught in global coordinates, and we'll just define the direction that your point is displaced, we'll call that theta equal to 0, then the cut is given by this formula. So T infinity is the intersection of the boundary of the past or the boundary of the future with infinity. And it has some angular dependence given by this expression. So these cuts are tilted with respect to the standard sort of t equals constant slices of your boundary. And you can see that if r goes to 0, the right-hand side diverges. That just says that the cut is given by t infinity equal to plus or minus pi over 2. That's what you expect because, well, by spherical symmetry, if you're at the origin, your cut is going to be at constant t, and it takes a coordinate time pi over 2 to get from the origin out to infinity in pure ADS. The other limit, when r naught goes to infinity, the right-hand side just becomes the tangent of theta, and so this says that t infinity, the cut is just t equal to theta. That's the light cone on the boundary, and that's what happens to the cut when you go all the way out to infinity. Now, by time translations and rotations, you get a d plus 1 dimensional space of cuts, because you can translate t up to any time t naught, you have the parameter r naught, and you can rotate to have the tilt in any of d minus 1 angles. So you get a preferred d plus 1 dimensional space of these cuts. Now in ADS there's no gravitational lensing, so there's no caustics, and all of these cuts are smooth. And there's a simple direct connection between these cuts and global causal relations between points in anti-de Sitter space. So in anti-de Sitter space, if two cuts do not intersect if and only if the corresponding points are time-like separated. They intersect at precisely one point if and only if the points are null separated, and they cross if and only if they're space-like separated. Now, that is not true in general for asymptotically ADS spacetimes, but some of it is true and enough to allow us to reconstruct the metric, as I will show you. OK, so now let me turn to how we reconstruct the conformal metric given the cuts. So as I said, the conformal metric is simply the metric up to an overall constant. So let's think about fixing a point, and the metric is determined up to this constant. Clearly, two conformally related metrics have the same light cone. Conversely, the light cone uniquely determines the conformal metric. A little bit more surprisingly, one can show that the conformal metric is uniquely fixed by any open subset of the light cone. So let me give you a quick argument for that. So let's take any d, if we're in a d+1 dimensional space, take d+1 linearly independent null vectors, vi, and we're going to view them as a basis for the tangent space. You can always do this because there's no vector which is orthogonal to all the null vectors. So you can form a basis of null vectors. Now, these vectors, of course, have zero norm, but you don't yet know their inner products. And we'll need to determine the inner products to fix the metric. So you can do that by taking any other set of null vectors, I'll call them wj, and expand them in terms of our basis null vectors v. And then the fact that w squared to 0 gives us a set of linear algebraic equations for these inner products. So let me give you just a little bit more detail. So we look at a point, the past light cone in a point, and we first pick d+1 null vectors, independent null vectors, and those are what we're calling v. And then we pick another set of null vectors, different set of vectors, w, expand them in terms of the v with some coefficients m. And then for each k, there's no sum here. For each k, w squared has to be 0 because it's a null vector. And therefore, we get these linear algebraic equations for the inner products of our basis vectors. And once you know the inner products between your basis vectors and their norm, which is 0, you've got the metric determined. Now, in fact, these equations can never determine the inner products uniquely. What you get is the inner product up to an overall constant rescaling, the same rescaling for all the inner products. And that's a homogeneous equation. So that says that you get the conformal metric and rather than the metric. OK, so as I say, if you take enough of these w's, you get a unique solution up to an overall constant. OK, another result that we're going to need is that if two cuts, C of P and C of Q, intersect at precisely one point, and both cuts are differentiable at that point, so we're not sitting at a cusp or a caustic, then the 2 points in the bulk must be null separated. And the idea of the proof is just that there's a unique inward-directed null geodesic, a unique orthogonal inward-directed null geodesic from each smooth point on a cut. So here is a cut, and there's some null geodesic into the bulk here. And so the statement is that if these cuts are tangent, then the null geodesic, which is orthogonal to this cut, is also orthogonal to that cut. And therefore, it must go through both P and Q. And therefore, P and Q must be null related. In fact, you can prove the converse, that if you have a null geodesic, which goes out to the boundary and hits the boundary at a point x, the cuts associated with each point on that null geodesic are all tangent at x. So now we're going to combine these two results I just mentioned and reconstruct the conformal metric just from the location of the cuts. OK, so on the left, I have a picture of space-time. On the right, I have a space of cuts. So we start in space-time with a bulk point P, and we have this cut C of P. Now, in general, there can be caustics, and so there could be a point here where two null geodesics from P meet up, and so that's a non-differentiable point C0. But we're going to avoid that. We're going to look at a smooth point X. And this cut, C of P, corresponds to a point, capital P, in the space of cuts. And then if I look at another cut, C of Q, which is tangent at X, that gives me another point in the space of cuts, capital Q. And by looking at all the cuts, which are tangent at x, I get a line in the space of cuts. And we're going to define that line to be null because of the property I just mentioned. Then you can move x or move to another point, y, where this cut C of p is still differentiable, maybe over here. And then you look at all the cuts tangent to the cut at y, and that will give you another line in the space of cuts, which you define to be null. You do that d plus 1 times, and you get these d plus 1 null vectors, which you're going to use for these VIs, your basis of the tangent space. And then you can determine the inner products by taking some other points and looking at other cuts tangent, and that gives you the w's. And then in that way, you construct the conformal metric at p, just from the space of cuts and which ones are tangent to which other ones. OK. Now I have to complete the story. So I've told you that if you have a space-time which is asymptotically anti-de Sitter, you can define this space of cuts. And given the space of cuts, you can reconstruct the conformal metric. But in holography, we want to get everything from the dual field theory. And so here's how you can do it. So we were heavily influenced by a very nice paper by Maldacena, Samin-Stuffin, and Zhibidov that came out last fall, I think called Looking for a Bulk Point. And there was earlier work by these authors. So the statement is that if you take the large n, large coupling limit, the usual classical bulk limit of the dual field theory, and you let O be any local CFT operator, and consider the time-ordered Lorentzian correlator of that operator. Now we need a d plus 2 point correlator. So the idea is that you have 2 points, z1 and z2 in the past, and d points in the future. And you ask, when is this correlator infinite? When does a correlator diverge? Well, these authors show that it diverges when there is a bulk point y, which is null related to every one of the boundary points. And if you send in high energy quanta from these two z's in the past, it can scatter, conserving energy momentum at y, into high energy quanta going out to these future points. When you have that, well, the bulk theory, local bulk theory predicts that there would be a singularity in the bulk correlator, and you take the limit and you get a singularity in the boundary correlator. So when this correlator diverges, of course it could diverge because of diagrams like that with the vertex y on the boundary. That would be an ordinary CFT type divergence, and we don't not interested in that. So if the correlator diverges for boundary points here, these x's and z's, and there is no boundary point y which satisfies these conditions, then there must be a bulk point. And so this is how you can identify a bulk point by singularities in these Lorentzian correlators. OK, I should maybe say that you need d plus 2 points here, because if your space-time is d plus 1 dimensional and you have only one boundary point, there's a d-dimensional space of bulk points null related to it. And so if you want to fix a unique bulk point, you need d plus 1 boundary points. That will fix uniquely a bulk point. But to conserve energy momentum at the vertex, you need another one. So that's good to look for d plus 2 point correlators. OK, but that structure is very similar to our cuts. Every point in the future and past cut of p is null related to the bulk point p. So we can now use that idea to determine the cuts. But we actually do two generalizations. So these papers worked in the vacuum, pure ADS. And so this was all scattering in pure ADS. And we're going to generalize it to an excited state corresponding to an asymptotically ADS space-time. There's actually an immediate advantage to doing this. In pure ADS, OK, so 2 points on the boundary can be null separated only if their time separation is less than pi. OK, I'm setting the radius of the sphere to 1 and like the ADS radius to 1. In pure ADS, light rays can go through the bulk in that same time pi. So you have to work hard to see whether your vertex can happen on the boundary or in the bulk. But the minute you go to an excited state and your space-time is not pure ADS, and provided the null energy condition is satisfied in the bulk, then the light rays which go through the bulk get delayed, and they always come out at a time bigger than pi. So if you have this Lorentzian correlator and you find singularities where the time difference between your future and past points are more than pi, then you know immediately it's coming from a bulk point and not from a boundary point. And secondly, we need to add one more point to the correlator and look at a d+3 point correlator. And now the idea is that we fix d+1 points in the future. So that uniquely fixes the vertex, because a point can be null related to d+1 points. That uniquely fixes y. But then we still want to have 2 points in the past, zi, that we can then rotate. We want to now deform them in space-like directions, keeping the correlator infinite. And so if you fix your future points, rotate your boundary points, keeping the correlator infinite, you will trace out the past cut. And clearly, you can time reverse it and trace out a future cut. A couple of comments. This procedure only works for points in the causal wedge of the entire boundary. So that means points which are both in the future and the past of the boundary. So in other words, you cannot use this to determine the sort of cuts of points inside black holes. Since the cut only corresponds to part of the light cone, remember I said some of the null GD6 have caustics and they move into the interior, momentum conservation at the vertex can mean that only part of the cut can be reconstructed this way. But that's OK, because you can get the conformal metric just from part of the light cone. And then finally, you can ask about perturbative corrections. The singularity is there in the classical limit. That's the usual large n limit. It's expected to remain with perturbative 1/n corrections are included, but not at finite n. Okay, so at finite n, we have real quantum gravity. We don't expect to locate points. So we're not going to be able to use this to say anything at finite n. All right, I'm running out of time, so I think that I will skip. One can say more from these cuts than just getting the conformal metric. So you can also say when some points are space-like separated and when some points are time-like separated. But I will skip that and just spend my last few minutes telling you about, one idea to determine the conformal factor and wrapping up. So this is something we're working on, but it's a sort of natural thing to do. So far, I've not assumed anything about the bulk equation of motion. Everything I've told you works for any bulk space-time which is asymptotically ADS. Now, we've determined the conformal metric from these light cone cuts. So that says we know what the Weyl tensor is in the bulk. If we know that there are no matter fields turned on, and if we use the Einstein equation in the bulk, that immediately fixes the Ricci curvature. So if we know the Ricci curvature and we know the Weyl curvature, then we know the entire curvature and the geometry in the bulk is fixed. But since we only need to determine one function, this conformal factor, you don't need the full set of Einstein's equation. You only need one component of it. Okay, so with some small amount of information about the bulk equations of motion, at least in this vacuum case, you can completely fix the metric and determine the conformal factor. So some open questions. We'd like to obtain other cuts from the CFT. I gave you one way to obtain the cuts for bulk points which are in the causal wedge, in causal contact with the boundary to the future and past. Can you do better? Well, here's just an existence proof that you can do better. If you have a spherical symmetric collapse to a black hole, of course, the boundary stress tensor is spherically symmetric. And the past cut of any point at the origin is fixed by the symmetry, because it has to be one of these spherical cuts. But that includes points inside the horizon. So at least in this simple case, we know what the past cuts of points inside the horizon at the origin are just from symmetry. So we'd like to do a lot better. Can you obtain matter fields in the bulk using these cuts? We have some ideas on how to do that. This is work in progress. OK, so to summarize, I told you there's a light cone cut for every point in causal contact with the boundary. These cuts can be determined from singularities in the gauge theory correlators. And the conformal metric in the bulk can be reconstructed just from the location of these cuts. And as I just said, if we use some information about the bulk equations of motion, in some cases we can determine the conformal factor as well. So these light cone cuts give us another way of representing the bulk in holography. And I view that as a very promising new direction to try to extend our current understanding of gauge gravity duality dictionary. Thank you very much.
Yeah, we have time for a few questions.
If you use the boundary correlators to define your cut, in a large N theory, there's not an infinitely strong coupling. So that would be dual to an alpha time corrected path. Would you still get these sharp sort of surfaces on the boundary?
Okay, at finite coupling you wouldn't, because then you would have real stringy things. You don't have local interactions. But at perturbatively in 1 over lambda, it should still be there.
Oh, sorry.
There's a similarity to twistor construction.
Yes.
You expect, therefore, that twistor space is the continuous space to get the holographic information from twistor space to the bulk data?
I am very intrigued by that connection, which, yes, when Ted Newman did this back in the 70s, of course, there was a very close connection. So he constructed a space of these special light cone cuts, and we called it heaven, and then there was a connection between heaven and twistor space. So anyway, in that case, there were some nice results on how to describe matter fields in terms of twistor space and stuff. So I'm hoping that some of that technology might come over, but we haven't really gotten very far in that direction.
Yeah, so I know another proposal that people have talked about in the past was using two-point functions to find the lengths of geodesics. So can you maybe comment on to what extent that resistance gets more or less information about the metric?
Yeah, so, okay, so if you have two-point functions, you get the lengths of certain space like geodesics. That's a case where you have to, well, you have to sort of basically invert it, right? You want to get the bulk metric from, well, it's part of this whole kinematic space. I mean, I don't know if you're talking about the kinematic space or you're talking about some more. Right. Okay. Yeah, I think that's a case where you still are sort of trying to extract the metric from integrals of the metric. And so there's some sort of inversion that has to be done. I view this as much more direct, because you get the cuts, and then just looking at how the cuts are tangent, you get the metric at the point. And this is good covariant in all dimensions and everything. So anyway, it's just another approach.
Okay. Andy,
yes, I have two questions. I didn't quite understand why doesn't gravitational lensing make the cuts self-intersect?
Okay, so you have two light rays. Let me just, I can go back and just show a quick. Okay, so here's a diagram. So here's a point P. You have two different null geodesics leaving P, but because of gravitational lensing, they end up hitting the boundary at the same point. Okay, so that's going to create a cusp in this cut. Okay, so that's the problem. That it's just not going to be smooth at that point because you have two different sort of orthogonal null vectors leaving that point.
I see. Could we continue that to a self-intersecting surface? I mean, if you take the things that are closer to the object that are lensed more?
Yeah, so if you do follow all of the light rays from P, what happens is that they do hit the boundary, but they hit the boundary down here. So you end up with a surface, so you could call it a self-intersecting surface. You get this cut, and then it continues down, and you get parts down here.
And then my second question is, it would seem, so in strictly infinite atom, there are small black holes which never evaporate. And you might think something dramatic would happen to the causal structure of these cusps when you have a small black hole. Can you use this as a diagnostic of whether there's a small black hole?
We're looking into that. Yeah, what we want to do now is to understand better. I mean, the cuts have these cusps have information also about how they were focused and everything, and yeah, there's a lot of information that we haven't used. So that's one of the things we're thinking about.
Well, I think we have to move on. Let's thank Gary again for the talk.